Hi everyone! In the last video we talked about the first two gas laws, Charles's law and Boyle's law. Now there are other gas laws that we haven't gone over, but in general those are the two that are probably the most useful. Now this next one is also very useful. This one is called the combined gas law. So this is going to combine Boyle's law and Charles's laws together to relate pressure, volume, and temperature to each other. So previously we learned that volume is proportional to temperature. So if the temperature of a gas increases, so does the volume. And if the temperature decreases, the volume decreases as well. And we also learned that pressure is inversely proportional to volume. So if the pressure of a gas decreases, the volume increases, and vice versa. So we can combine the two laws we learned previously, and we get the equation in the middle of the slide here. So here we have that an initial pressure times an initial volume divided by an initial temperature is equal to a final pressure times a final volume over a final temperature. Now we're going to assume that the amount of the gas is the same throughout this experiment. Now in this law, temperature has to be in Kelvin, just like we saw before. So remember, if you're given temperature in degrees Celsius, you have to convert it to Kelvin first. So let's practice using this law. So let's say that a gas has an initial pressure, P1, equal to 1 atmosphere. So that's our first data point there. And it has an initial volume, V1, of 0.5 liters. And then an initial temperature of 298 Kelvin. Then let's say the pressure is increased, so P2, it's increased to 1.5 atmospheres, and the volume increases to 1.0 liters, so that will be V2. And we want to figure out what is the final temperature. Okay. Now, earlier we saw that the combined gas law gives us pressure times volume over temperature for the initial state, and that should equal pressure times volume times temperature for the final state, state 2. Now we're trying to solve for T2, so we need to rearrange our equation. So what we can do is we can rearrange this equation to start. So what I might do is multiply both sides by T2, and that way T2 will cancel on the right, and now it's in the numerator on the left-hand side. Now next, if we want to still highlight or isolate T2, we have to get rid of P1 times V1 over T1. So what we actually need to do is multiply by the reciprocal of that fraction on both sides. So we'll multiply by T1 over P1 times V1 on both sides. So on the left-hand side, T1 will cancel, and then P1 times V1 will cancel. And now let's write this a little more neatly down below. So on the left-hand side, all we have left is T2. On the right-hand side, it looks like we have P2 times V2 times T1 all over P1 times V1. All right, so getting a little bit of our algebra practice in there, working with fractions and moving them around. So now that we have our rearranged equation, we can plug in our values. Now, if you prefer plugging in your values first and then rearranging, that is totally fine, whatever works for you. There's multiple ways to solve the same problem. Okay, so let's plug in our values. So P2 is 1.5 atmospheres. And we're multiplying that by V2, which is 1 liter. And then T1, which is 298 Kelvin. And then we'll divide by P1, which is 1 atmosphere, and multiply that by V1, which is 0.5 liters. All right, so let's make sure our units cancel. So atmospheres cancels with atmospheres, liters cancels with liters, and we're left with Kelvin, which is what we want. We want our final temperature value, and that unit should be in Kelvin. Okay, so in our calculators, we're just going to plug in 1.5 times 1 times 298, and then we'll divide by 1 times 0.5. And I recommend putting parentheses around the denominator if you have more than one value. Otherwise, your calculator might assume that you're dividing by 1 and then multiplying by 0.5. So sometimes I put parentheses around that denominator just so it's clear in the calculator what the value is. Okay, so when I plugged this into my calculator, I got a value of 890 Kelvin. All right. Now, with the combined gas law, it's a little harder to tell if your temperature would increase or decrease based on the changes in pressure and volume. So it's not as easy to tell what to expect in this case. But our final answer, let's see, has 2 sig figs, which is good because most of our values had 2 sig figs. All right, so the combined gas law is not so bad. You just plug in your values, and occasionally you might have to rearrange your equation. Now let's go on to the next law called the ideal gas law. So this is the one gas law that relates all of the independent properties of a gas under any condition. So earlier we saw laws where we considered a change in state. So we said, oh, we have our initial state and our final state. But the ideal gas law considers a gas at a particular moment. So this gas law is called, again, the ideal gas law. And we can see it in the middle here. We've got pressure times volume, and that's equal to the amount of gas in moles, that's the lowercase n, times an ideal gas constant, which is R. So that's this capital R, and we'll talk about that in a second. And then we'll multiply that by temperature, T. So again, notice we don't have an initial state and a final state for the gas. It's just going to be at one particular state. All right, so now we can relate pressure, volume, amount, and temperature to each other in one law. But let's talk about that ideal gas law constant, R. So R is going to depend on which units we're using. Now, typically, we use liters and atmospheres for volume and pressure, respectively. So when that's the case, R is going to equal 0.0821. And then the units, there's a lot of units, so bear with me. We have liters times atmospheres in the numerator. And then in the denominator, we have moles times Kelvin. Now, what if we want to use a different unit? So let's say, for example, instead of atmospheres, we want to use millimeters of mercury. that's actually going to change the value of R, so the ideal gas constant, because remember, 1 atmosphere is equal to 760 millimeters of mercury. So if we're using that unit, R becomes 62.4 liters times millimeters of mercury over moles times Kelvin. Now, I also want to let you know I'm going to give you these values on quizzes and exams. So I will provide these values. So you don't have to memorize these, don't worry. I'm also going to give you the equations for the gas laws, so you don't have to memorize all of these different equations either. You just have to know when to apply them and how to use them. All right, so let's do an example problem where we use the ideal gas law. So let's say we're trying to figure out what is the temperature of a 0.52 mole sample of gas with a pressure of 1.2 atmospheres and a volume of 10.7 liters. So maybe this is a gas that's inside of a container, and we're trying to figure out what is the temperature inside of that container. Well, since we already know the amount of gas, the pressure, and the volume, we can use the ideal gas law. Now let's write down everything we have so far. So we have the amount, N, 0.52 moles. We have the pressure, capital P, 1.2 atmospheres. And we have the volume, V, 10.7 liters. Now, since we're using atmospheres as our pressure unit, we can use the constant R that's equal to 0.0821 liters times atmospheres over moles times Kelvin. So again, that was given on the last slide. So I just took this value here. And I knew to use that value because, again, we're using the unit of atmospheres for pressure. So I didn't want to use the one that uses millimeters of mercury. Now we're trying to solve for temperature. So again, the equation here is PV equals nRT. Now, if we want to isolate temperature T and solve for that, we need to rearrange our equation. So in order to do that, we should divide both sides by nR. So temperature will equal PV over nR. All right, so now we can plug in our values. So pressure is 1.2 atmospheres. And we're multiplying that by volume, which was 10.7 liters. Then we're going to divide that by the amount of gas, 0.52 moles, and the gas constant, 0.0821 liters times atmospheres over moles times Kelvin. Now let's double check that our units cancel appropriately. So we have atmospheres in the numerator and the denominator. We have liters in the numerator and the denominator. And then if we just look at the denominator, we have moles canceling. And then we have K. K is in the denominator of a denominator. So how does that work? So let's kind of off to the side. If we have 1 over K, that's essentially equal to 1 over K to the negative 1. And you might remember from your math classes, if you have a negative 1 exponent in the denominator, that actually tells us that this is equal to K to the 1. So just K. So really, the unit that's way down here, K, is actually up here in the numerator. So just some tricky math tips that we can use to simplify things. Okay, so in our calculator, we're going to plug in 1.2 times 10.7 and then divide that by 0.52 times 0.0821. And we just figured out that our final unit is Kelvin. And that makes sense because we're solving for temperature. All right, so when I plug this into my calculator, I get a value of 300.76 Kelvin. Now let's think about sig figs. How many sig figs should our answer have? Well, it looks like most of our values have 2 sig figs. Volume has 3, the gas constant has 3, but again, when we're multiplying and dividing, we want to have the least number of sig figs. So we're going to limit our value to 2 sig figs here. And there isn't really a good way to round this to give us 2 sig figs, so let's write this in scientific notation. So 3.0 times 10 to, let's see, the 1, 2, second. So it seems a little odd to write a temperature in scientific notation, but you can do that if you need to. All right, so now I'm going to give you a problem to try on your own. So what is the pressure of a 0.32 mole sample of gas in a 6.2 liter container with a temperature of 25 degrees Celsius? So see if you can solve this on your own, and then we'll go over it together. Okay, so let's list out everything we're given. So we're given 0.32 moles, so that would be N, the amount. We're given 6.2 liters, which is the volume. And we're given the temperature. But we're given the temperature in degrees Celsius, so we probably want to convert that to Kelvin. But remember, to convert this to Kelvin, we just need to add 273. So that will give us 298 Kelvin. Now we're solving for pressure. We don't know what that is, but we do know what the gas constant is. Now you could use either gas constant that we talked about. Because, for example, let's go back. If you use the first gas constant, your pressure unit will be in atmospheres at the end of your calculation. But if you use the second one down here, your pressure will be in millimeters of mercury. So whichever one you want to use, you can use. It'll just affect your unit and the value of the pressure. I personally like using the unit of atmospheres, so I'm going to use the first conversion factor, gas constant. So 0.0821 liters times atmospheres over mole times Kelvin. Okay, so again, we're going to use the ideal gas law because we have all the right components for that. But we want to isolate pressure because that's what we're solving for. So let's divide both sides by volume. So that'll cancel on the left. And that tells us that pressure is equal to nRT over V. Okay, so let's plug in our values for nRT over V. So we've got 0.32 moles times our gas constant. times the temperature, 298 Kelvin. And then we're going to divide by 6.2 liters. Okay, so let's cancel some units. So it looks like we have moles in the numerator and then in the denominator of our gas constant. So those will cancel. Same for Kelvin. And then it looks like liters is in the numerator of our gas constant and then in the denominator of our equation. So those will cancel and we're left with atmospheres. Perfect. Okay, so now we just have to multiply 0.32 times 0.0821 times 298 and divide by 6.2. And our final unit is atmospheres. Now when I plug this in, I get 1.3 atmospheres. And I'm going to stick with 2 sig figs for this problem, so I rounded up. Now, let's say that you used the other gas constant, the 62.4 gas constant. You should get a pressure of about 988 millimeters of mercury. So if you did it that way, that's totally fine. You're just going to get a different value because you have a different unit. All right, so kind of going back through all of our gas laws, let's go back to our first one, Boyle's law. So with Boyle's law, if you're given pressure and volume for an initial state and a final state, you know to use Boyle's law. The other one we saw was Charles' law. So if you're given volume and temperature for an initial state and a final state, you know to use Charles' law. Oops. And then we went over the combined gas law. So if you're given pressure, volume, and temperature for an initial state and a final state, you'll know to use the combined gas law. And then finally, with the ideal gas law, if you're given pressure, volume, amount, and or temperature, you'll know to use the ideal gas law. And one of those, obviously, you're going to be solving for. Now, again, I'm going to give you these gas laws on a quiz or an exam, so you just have to figure out which equation you need to use for the problem you're working on. Okay, now in the next video, we'll go over a couple of other things about gases, and that'll be it for Chapter 8. So I will see you in the next video.